Hi students, our today's topic of discussion is inter-symbol interference and raised cosine function. We already discussed in our first lecture of baseband digital data transmission about the inter-symbol interference. Still, I will give a short review on that, and after that I will discuss the raised cosine function. So inter-symbol interference, as you see here, this is the interference due to the channel, dispersion inside the channel. That means whenever the signal is passing, that means digital signal, it is passing through a band limited channel. What is band limited channel? Means only a particular band of frequencies are available. That means baseband data. Baseband data means the original data. Okay, it may be some voice signal or maybe some video signal like TV. Okay, so as we know in our previous section, it is a previous class, actually class lectures, it has been covered. Okay, so what is basically the band limited thing? Band limited signal means baseband signal means the original signal. That means it may be some original voice signal or original some video signal, and that will have some particular band of frequencies, that is called the baseband signal. And when the baseband signal is basically digitized with the help of quantizer, with the help of sampler, then quantizer, different stages are there as we know earlier, and then coding is there. Okay, so after the coding there are two types of coding. Okay, one is encoding of the data, then channel encoding is also there. So after the coding of the data, different type of coding schemes are there, like binary schemes and all, maybe gray code. So different types of Hamming code is there. So different codings are there. So after different codings, the basically data will be digitized, fully digitized. So after sampling, there comes the quantization. After quantization comes the encoding or simply coding. So these are the three basic stages of digitizing an analog data. So this digital data cannot be processed directly, cannot be thrown into the channel. Okay, that's why the analog, whatever digital data you are getting, that data is to be basically converted into electrical waveform. Okay, and that's why we use the pulse amplitude modulation. Okay, so the digital input data will come inside, after encoding it will come inside the pulse amplitude modulator, and it will modulate the data, and it will make electrical waveforms to pass through the channel. Whenever it is passing through the channel, it will, due to the dispersion basically inside the channel, inter-symbol interference will occur. As we know in our previous lecture, we have already studied all those things. Still, I am giving a short review or recap on the previous lecture. Otherwise, you will not be able to understand the concept properly. Okay. So obviously, discrete pulse amplitude modulation technique is used here. Okay. And what are the channels? This is basically, what is this? This is modulation, is nothing but the channel, a different type of channel encoding schemes. So we already know the channel encoding schemes. Okay, NRZ is there, RZ is there, Manchester coding is there. Okay, so polar, unipolar, bipolar, so many types of coding we already know. This is second phase of coding. This is called the channel encoding. M-array coding is also there. These are all channel encodings, and this is done in this part, pulse amplitude modulation part. This channel encoding is done. Okay, so the channel encoded data passes through the channel. Okay, and it will have some dispersion, and due to dispersion, ISI will be produced. Okay, so we already discussed the ISI. Okay, XT, that is the input with the help of block diagram. This is the block diagram. Okay, input, binary input is there, pulse generator. That means this is the PAM, pulse amplitude modulator. Here the channel encoding will happen. Okay, and there is transmitting receiver, channel, receiving filter, and decision device is there. It is the receiver side, this is the transmitter side, this is the channel. Okay, so in this channel there will be ISI, inter symbol interference is there, and I have already discussed it, what is ISI and how this is the expression of ISI, YT, YK, everything I have discussed in our previous lecture, and from there we find out this extra thing, this is the ISI. And now I want to reduce the ISI. This, due to the dispersion in the channel, the data is being distorted. This is the ISI basically. Okay, after the channel encoding, when the data is digital data in electrical waveform, when it is passing through the channel, then it will face the inter-symbol interference, and whenever it will be received by the receiver section, then the receiver section will basically face the problem. Okay, so obviously the receiver section has to detect is there any ISI or not, and it has to eliminate the ISI accordingly. Okay, so what are the processes to eliminate the ISI? Okay, so today we will be discussing the processes to eliminate ISI. Ideal solution for inter-symbol interference. So what is the ideal solution? Ideal solution means PF. What is PF? PF and PT. PT is the time domain representation of P function. PF is the frequency domain representation of the P function. Okay, what is P function? What is P function? Let me see. Let us have a look on that. This is the P function. That means in the output side of the receiver input, output side of the receiver, it is wrong. It is the input side, YTI. If we go back here, okay, YT, this is the receiving filter, and YT is being receiving filter output. It is not, if you go to this section, see, this is not the exact output of the receiver. This is the output of the receiving filter only, YT. Okay, don't be confused. It is not the receiver output. It is the output of the receiving filter of the receiver section. Okay, YT. And this is a sampler is there. So YT will be converted into YKT. Okay, that means digitized version of the receiving filter output. That is YT. Okay. So after that there will be decision making unit. See. After that YKT, there will be decision making unit. There will be decoding of the data. Okay, decoding is, there will be decoding of the data henceforth. Okay. So first of all, from the channel the data will come and it will be received by the receiving filter, and it will filtrate some that means unwanted frequency band elements. Okay. And filtered output is this one. Then it will go to the decision device, and subsequently it will go to the decoder portion and all. Okay. So see, this is inter-symbol interference. So YT, is it clear what is YT? And in the expression of YT there is function PT. Okay, so the frequency domain version is PF. Okay, so basically a signal waveform that produces zero inter-symbol interference is defined by the sync function. So sync function in time domain PT, if the PT, that means receiving, in the receiving filter output, the YT function, if it contains PT in such a way that PT is a sync function. This is called the sync function, where B0 is 1 by 2 TB. Okay, so what is B0 and what is TB? TB basically, is basically the sampling period, time period. Okay, after the receiving filter, that is the sampling time period. So 1 by 2 TB, that is giving B0. Okay, the parameter B0 is called the Nyquist bandwidth, which is equal to the minimum transmission bandwidth needed for zero intersymbol interference. So this is the minimum bandwidth required. Okay, so if you take lesser bandwidth, if your data bandwidth is lesser than this bandwidth B0, then obviously there will be intersymbol interference. So we have to keep it in mind that we have to basically send the data, and the data bandwidth should be, okay, the B0 value. Minimum transmission bandwidth should be B0. Okay, the minimum transmission bandwidth should be B0. Okay, and B0 is equal to 1/2 of the bit rate of the sampler. Okay, in the receiving portion, transmission portion, both sampler bit rate should be TB. Okay, so B0 represents the maximum, the minimum transmission bandwidth required required for the data for zero intersymbol interference. So PF, that is frequency, in frequency domain, if I convert it, then PF is 1 by 2 beta 0, the mod value of the frequency when it is in between 0 to B0. That means maximum B0 frequency element is coming into your data. Okay, it is present in your data. Okay, maximum B0 frequency element. This is the maximum value. So whenever, this is basically band limit of your transmitted data. Okay, so you have to be sure that the data frequency cannot cross B0. So when it is B0, up to B0, 0 to B0, then the PF is 1 by 2 B0. Okay, the gain is, you are getting high gain, and whenever it is outside the limit, the frequency passes, means greater than B0, then 0 value is there. Okay. Therefore, no frequencies of absolute value more than half the bit rate are needed. Okay. Is it clear to you? So, half the bit rate, half of the bit rate, so it is required. Okay. The function PT and PF are shown comparing PT with the response of the ideal low pass filter. See, PT response, if you see this response, it completely matches with the ideal low pass filter. Okay. To an impulse input. That means if you give an impulse input into the ideal low pass filter, you will get this type of equation. Okay, is it clear to you? See, this is the graph of ideal low pass filter. Okay, that is the frequency, this is the frequency axis, and the amplitude of the gain of the filter. Okay, so up to this you are getting a flat high gain. Okay, after that it is 0. Now see the PT function. The PT function, it is basically, the gain is high from plus B0 to minus B0. Otherwise it is gradually, after every TB, see, every TB it is crossing the 0. Okay, so it is slightly oscillatory in nature. So if I create a PT like this, that means sinc function, this is the sinc function, right? So if I can make PT as a sinc function, then my problem is solved. That means the ISI will never ever bother me. Okay, but practically it is impossible, okay, to make a sinc function. That means what are the practice? See, the ideal choice of pulse shape for PT, describe the equation 5.7, solves the problem of ISI. Okay, so your problem of ISI is solved in this way. But the ideal is for the ideal pulse shape for the for the low pass filter is a flat top. I already shown you. Okay, and 0 elsewhere. So it is physically unrealizable. So the sinc function, getting a sinc function, it is very difficult. Okay, so that's why to